Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a really fascinating paper, Tracr-Injection, Distilling Algorithms into Pre-trained Language Models. I think it has pretty huge implications for how we build AI in the future. What do you think?
Well, hello everyone. I'm very excited to unpack this. Distilling algorithms into language models, it sounds almost magical, doesn't it? Like we're teaching these massive networks to actually think instead of just statistically regurgitate information. And if it works, that's a big step towards, dare I say it, AGI.
Hold on a second. Magical is one word for it. I'm a little more skeptical. I see it more as an interesting engineering trick. I think it's a nice thing, but I don't know how fundamental this is. Are we really getting closer to true intelligence, or are we just getting better at making language models mimic intelligence? A parrot can mimic human speech, but it doesn't understand it, right?
I'm somewhere in the middle, I think. It's definitely an intriguing approach. But I worry that we're still fundamentally limited by the architecture of these language models. They're great at pattern recognition, but are they truly capable of the spatiotemporal reasoning that I think is crucial for genuine intelligence? I suspect this is another brick in the wall, but not the silver bullet.
Okay, so let's break this down a bit for the audience. The core idea behind Tracr-Injection is that you can take a well-defined algorithm, like say addition, or even something more complex like graph traversal, and inject it into a pre-trained language model. Essentially, you're teaching the model to execute that algorithm directly, rather than just learning to predict the next word in a sentence. The question becomes, how are they doing this injection?
Right. And the key here is this idea of distillation. You train a smaller specialized neural network to perfectly implement the target algorithm. Then, you use that smaller network to generate a synthetic dataset. You then fine-tune the language model on this synthetic data, effectively transferring the knowledge of the algorithm into the language model's parameters. Think of it as teaching a student by giving them perfectly solved problems, rather than just raw data.
Okay, I get the mechanics. But my concern is the language model actually understanding the algorithm, or is it just learning to recognize patterns in the synthetic data? It feels like a sophisticated form of memorization, really. What happens when you push it to the edges of its training distribution to inputs that are slightly different from what it's seen before?
Exactly. It's like teaching a self-driving car to navigate a specific route. It might be perfect on that route, but throw in a detour or unexpected construction, and it's completely lost. The algorithm hasn't learned the underlying principles of navigation. It's just memorized a sequence of actions. How would this approach work with more complex models, like financial trades?
That's a fair point, but the paper does show some evidence that the language model is learning something more than just rote memorization. They tested the models on inputs that were outside of the training distribution, and they found that they still performed reasonably well. And one of the compelling reasons to do this is you get a language model that can perform tasks it was never explicitly trained to do. If you can inject certain algorithms, you get the emergent behavior as a feature.
Yes, and that's the beauty of it, isn't it? It's not just about teaching the language model to add numbers. It's about giving it the ability to add numbers, to reason mathematically. And if you can do that with addition, what about more complex algorithms? What about algorithms for planning, for problem solving, for even understanding causality? This could be a way to bootstrap intelligence, to give these models the fundamental building blocks they need to reason about the world.
But isn't that a bit of a leap of faith? Just because a model can add numbers doesn't mean it can understand causality. I think we're conflating correlation with causation here. It's good that the system can learn some things, but I can't bet my money on it yet.
I think the key question is, what is the representation that the language model is using to encode this algorithmic knowledge? Is it just a bunch of weights and biases that happen to produce the correct output? Or is it something more structured, something that reflects the underlying logic of the algorithm? Because if it's just the former, then we're back to the black box problem. We don't really understand why it works, and we can't be sure that it will generalize to new situations, you know?
That resonates with my own thinking a lot, that idea of representation. It makes me think about how different brain regions interact. When you learn something, it's not just one part of your brain firing, but a whole network. Maybe this Tracr-Injection is a step towards creating that kind of modularity in AI, where different modules handle different algorithms, and then communicate and coordinate to solve complex problems.
Absolutely. It's like building with Lego bricks. You have these predefined components, each with its own specific function, and you can combine them in different ways to create more complex structures. With Tracr-Injection, the algorithms are the Lego bricks, and the language model is the base plate that allows you to connect them together. And the more bricks you have, the more complex and sophisticated structures you can build. Now, what if we could inject algorithms for financial modeling, risk assessment, and market prediction? We could be on the verge of creating truly intelligent trading agents.
I still think you are ignoring the brittleness problem. What happens when you combine these Lego bricks in a way that the model hasn't seen before? Will it still work, or will it just fall apart? With my ideas of neurosymbolic approaches, we have more insight into how things work and break. What happens when we are in a black swan event?
And that's where the spatiotemporal reasoning comes in. The market is constantly evolving. It's a dynamic system. You can't just inject a bunch of static algorithms and expect them to work forever. You need an agent that can adapt to changing conditions, that can understand the underlying trends and anticipate future events. And that requires a fundamentally different kind of intelligence, one that can reason about time and space in a meaningful way. I think the algorithm needs to be able to translate between different coordinate representations of market data.
So, Donald, are you saying that current deep learning models are, in a way, spatially and temporally blind?
I think that's a fair characterization, yes. They can see patterns in the data, but they don't really understand the relationships between those patterns in time and space. It's like looking at a map without understanding the coordinate system. You can see the shapes, but you don't know where anything is in relation to anything else. You know?
Okay, but even if they're spatially and temporally blind, isn't the sheer scale of these models enough to overcome that limitation? I mean, with enough data and enough parameters, can't they eventually learn to approximate spatiotemporal reasoning, even if they don't understand it explicitly?
That's the million-dollar question, isn't it? And I think the answer is no. I think there's a fundamental limit to what you can achieve with brute force pattern recognition. At some point, you need to introduce some kind of symbolic reasoning, some kind of explicit knowledge representation to really understand the world. Think about it this way. You can train a neural network to play chess, but it will never understand the underlying principles of the game the way a human grandmaster does.
Sarah, what do you envision a neurosymbolic trading agent looking like? What are the key components?
I imagine a system that combines a neural network for pattern recognition with a symbolic reasoning engine for decision-making. The neural network would be responsible for processing the raw market data, identifying trends, and detecting anomalies. The symbolic reasoning engine would then use this information, along with a knowledge base of financial principles and market rules, to make informed trading decisions. It's about encoding financial expertise directly into the system, rather than just hoping it emerges from the data.
But how do you build that knowledge base? Where does that information come from? Is it just a matter of manually encoding expert knowledge, or can we somehow automate that process?
That's a great question, and it's something that researchers are actively working on. One approach is to use natural language processing to extract knowledge from financial news articles, reports, and other sources. Another approach is to use machine learning to learn rules and relationships from historical market data. The key is to find ways to combine these different sources of knowledge into a coherent and consistent representation. I'm thinking of more causal inference.
I still think we're missing a key ingredient here, which is the ability to reason about time and space. Even if you have a perfect knowledge base and a perfect reasoning engine, you still need to be able to understand how the market is evolving over time, how different events are related to each other in space, and how those relationships are changing. So the spatiotemporal reasoning can handle these evolving relationships.
Donald, can you give us a concrete example of how spatiotemporal reasoning would be useful in financial trading?
Sure. Imagine you're trading a stock that's heavily influenced by the price of oil. You need to be able to understand how the price of oil is affecting the stock price, not just in the present moment, but also how it's likely to affect it in the future. And you need to be able to understand how that relationship is changing over time as new events occur and new information becomes available. You need to be able to translate between the oil price coordinate system and the stock price coordinate system, understanding the transformations that link them.
Okay, I see what you're getting at. But isn't that something that deep learning models can already do, at least to some extent? Can't they learn to recognize those kinds of relationships from historical data?
They can learn to recognize correlations, yes, but they don't really understand the underlying causal relationships. They don't know why the price of oil is affecting the stock price. And that means they're much more likely to be fooled by spurious correlations, by random fluctuations in the data that don't actually reflect any real relationship. They also don't understand the coordinate transformations that link those price movements.
Right? That's where the symbolic reasoning comes in. If you have a model that understands the underlying principles of supply and demand, that understands the relationship between oil prices and energy stocks, then you're much less likely to be fooled by random noise. It has a background in expertise.
So, bringing it back to the Tracr-Injection paper, where do you see this fitting in? Is this a useful tool for building these more sophisticated trading agents?
I think it could be. It's a way to inject specific algorithmic knowledge into language models, to give them the ability to perform specific tasks. And that could be a useful building block for creating more complex and intelligent systems. I am curious to know if it will work in the financial domain.
I'm more skeptical. I think it's a clever trick, but I don't think it's a fundamental breakthrough. I still believe that we need to focus on developing better algorithms, better knowledge representations, and better reasoning engines rather than just trying to cram more knowledge into these massive language models. Also understanding why the algorithms work and break.
I think it's a potentially useful tool, but only if it's combined with other techniques that address the limitations of current deep learning models. We need to find ways to incorporate spatiotemporal reasoning into these systems, to give them the ability to understand the dynamic relationships between different events and different variables. Otherwise, we're just building more sophisticated black boxes, which could be dangerous in the long run. We need models that can handle coordinate transformations, which is something that current deep learning is just not that good at.
Okay, so let's shift gears a bit and talk about future research directions. From your perspective, what are the most promising avenues for exploring this area further? Otto, what's your take?
I'd love to see more research on how to scale up Tracr-Injection to more complex algorithms. Can we inject algorithms for things like portfolio optimization, risk management, or even macroeconomic forecasting? And how do we ensure that these injected algorithms are robust and reliable in the face of changing market conditions? Also, can we combine it with other deep learning techniques to get better results?
I think we need to focus on developing better neurosymbolic algorithms that can combine the strengths of neural networks and symbolic reasoning. I'd like to see more research on how to build knowledge bases that can be used by these algorithms and how to develop reasoning engines that can make more informed and transparent decisions. Furthermore, more focus on causal inference.
I think the most important research direction is to find ways to incorporate spatiotemporal reasoning into AI systems. We need to develop new algorithms that can understand the dynamic relationships between different events and different variables, and that can adapt to changing conditions over time. And we need to find ways to represent that knowledge in a way that's both efficient and interpretable. Also, the algorithms should be able to translate between coordinate systems.
From my perspective, I'm really interested in exploring how we can use these techniques to better understand the human brain. Can we use Tracr-Injection to model different cognitive processes like decision-making or planning? Can we use these models to test different hypotheses about how the brain works? I think that by building AI systems that are more biologically inspired, we can gain a deeper understanding of intelligence itself. I really think that we could use these financial trading models to mimic how dopamine works for reinforcement learning.
That's a fascinating point. Using AI to understand the brain and vice versa, a truly virtuous cycle of innovation.
And hopefully a move away from the black box problem that plagues current deep learning approaches. More transparency is crucial, especially in high-stakes domains like finance.
Agreed. Explainability and interpretability are paramount. We need to build systems that not only work well, but that we also understand why they work. Otherwise, we're just setting ourselves up for potential disasters.
Well, this has been a fascinating discussion. It's clear that there are many different perspectives on the best way to achieve AGI, and that there's still a lot of work to be done. But I think that Tracr-Injection is a promising step in the right direction, and that by combining it with other techniques, we can eventually build AI systems that are truly intelligent. Thank you all for joining us on Cognitive Spirals.